Chapter 5. Symbols. Quote, "One cannot escape the feeling that these mathematical formulae have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers, that we get more out of them than was originally put into them." Heinrich Hertz. Algebra, in the broad sense in which the term is used today, deals with operations upon symbolic forms. In this capacity, it not only permeates all of mathematics, but encroaches upon the domain of formal logic and even of metaphysics. Furthermore, when so construed, algebra is as old as man's faculty to deal with general propositions, as old as his ability to discriminate between some and any. Here, however, we are interested in algebra in a much more restricted sense, that part of general algebra which is very properly called the theory of equations. It is in this narrower sense that the term algebra was used at the outset. The word is of Arabic origin. El is the Arabic article the, and jabar is the verb to set, to restitute. To this day the word algebrista is used in Spain to designate a bone setter, a sort of chiropractor. It is fitting that the word algebra should be the adaptation of the title of a book written by Muhammad ben Musa al-Khwarazmi, the same al-Khwarazmi who, as we saw, contributed so much to the development of positional numeration. The full title of the book is Al-Jabar wal-Muqabbala, an exact translation of which would read, "On Restitution and Adjustment." Ben Musa used restitution in the same sense in which we today use transposition, i.e. the shifting of the terms of an equation from one side to the other, as for instance the passing from 3x plus 7 equals 25 to 3x equals 25 minus 7. Traces of primitive algebra are found on the clay tablets of the Sumerians, and it probably reached quite a high degree of development among the ancient Egyptians. Indeed, the Papyrus Rind, of not later date than the 18th century BC, deals with problems in distribution of food and other supplies, problems which lead to simple equations. The unknown in these equations is designated by how, a heap, addition and subtraction by the legs of a man walking either towards the symbol of the operand or away from it. The papyrus is signed by one Ahmes. Ahmes, however, judging by the many gross errors in the text, was a mere scribe who understood little of what he was copying, so it is conjectured that the state of ancient Egyptian knowledge was higher than this papyrus would lead us to believe. Be this as it may, that Egyptian algebra antedates the papyrus by many centuries. It is generally true that algebra in its development in individual countries passed successively through three stages: the rhetorical, the syncopated, and the symbolic. Rhetorical algebra is characterized by the complete absence of any symbols, except, of course, that the words themselves are being used in their symbolic sense. To this day, rhetorical algebra is used in such statement as, "the sum is independent of the order of the terms," which in symbols would be designated by A plus B equals B plus A. Syncopated algebra, of which the Egyptian is a typical example, is a further development of rhetorical. Certain words of frequent use are gradually abbreviated. Eventually, these abbreviations become contracted to the point where their origin has been forgotten, so that the symbols have no obvious connection with the operation which they represent. The syncopation has become a symbol. The history of the symbols plus and minus may illustrate the point. In medieval Europe, the latter was long denoted by the full word minus, then by the first letter M duly superscribed. Eventually, the letter itself was dropped, leaving the superscript only. the sign plus passed through a similar metamorphosis. The reader is referred to the accompanying table for a chronological history of the standard symbols. Greek algebra before Diophantus was essentially rhetorical. Various explanations were offered as to why the Greeks were so inept in creating a symbolism. One of the most current theories is that the letters of the Greek alphabet stood for numerals, and that the use of the same letters to designate general quantities would have obviously caused confusion. It is pointed out that Diophantus took advantage of the fact that in Greek the sound sigma has two different forms. One designated 60, but the end sigma had no numerical value, and it is for this reason that Diophantus chose it to symbolize the unknown. The truth of the matter is that the Diophantine symbol for the unknown is more likely a syncopation of the first syllable of the Greek word arithmos, number, by which name he designated the unknown of a problem. Besides, the theory seems to disregard the fact that only the small letters of the Greek alphabet were used as numerals. The Greeks had at their disposal the capital letters which they could, and indeed did, use as symbols. Yet those symbols were never used in an operational sense, but merely as labels to designate different points or elements of a geometrical configuration. Such descriptive symbols are used by us today in identifying various points of a geometrical figure, and it should be remembered that we inherited this custom from the Greeks. No, Greek thought was essentially non-algebraic because it was so concrete. The abstract operations of algebra, which deal with objects that have purposely been stripped of their physical content, could not occur to minds which were so intensely interested in the objects themselves. The symbol is not a mere formality, it is the very essence of algebra. Without the symbol, the object is a human perception and reflects all the phases under which the human senses grasp it. Replaced by a symbol, the object becomes a complete abstraction, a mere operand, subject to certain indicated operations. Greek thought was just beginning to emerge from the plastic state, when the period of decadence set in. In these declining days of Hellenic culture, two persons stand out. Both lived in the 3rd century of our era, both hailed from Alexandria, both sowed the seeds of new theories, far too advanced to be absorbed by their contemporaries, but destined to grow into important sciences many centuries later. The porisms of Pappus anticipated projective geometry. The problems of Diophantus prepared the ground for the modern theory of equations. Diophantus was the first Greek mathematician who frankly recognized fractions as numbers. He was also the first to handle in a systemic way not only simple equations but quadratics and equations of a higher order. In spite of his ineffective symbolism, in spite of the inelegance of his methods, he must be regarded as the precursor of modern algebra. But Diophantus was the last flicker of a dying candle. Over the Western world spread the long night of the Dark Ages. The seeds of Hellenic culture were destined to sprout on alien soil. The Hindus may have inherited some of the bare facts of Greek science, but not the Greek critical acumen. Fools rush in where angels fear to tread. The Hindus were not hampered by the compunctions of rigor. They had no sophists to paralyze the flight of their creative imagination. They played with number and ratio, zero and infinity, as with so many words. The same sunya, for example, which stood for the void and eventually became our zero, was also used to designate the unknown. Yet the naive formalism of the Hindus did more to develop algebra than the critical rigor of the Greeks. It is true that theirs was syncopated algebra, par excellence. The symbols were merely the first syllables of the words designating the objects or operations. Nevertheless, they had symbols not only for the fundamental operations and equality, but for negative numbers as well. Moreover, they had developed all the rules for the transformation of simple and quadratic equations. The types of problems they handled were simple enough, and are really typical of that stage of algebra. We quote two from Lilavati, a treatise on general theology written in the 8th century of our era. Quote, Out of a heap of pure lotus flowers, 1/3, 1/5, and 1/6 were offered respectively to the gods Siva, Vishnu, and the sun. 1/4 was presented to Bhavani. The remaining 6 flowers were given to the venerable preceptor. Tell me quickly the whole number of flowers. End quote. Quote, a necklace was broken during an amorous struggle. 1/3 of the pearls fell to the ground, 1/5 stayed on the couch, 1/6 was found by the girl, and 1/10 recovered by her lover. 6 pearls remained on the string. Say of how many pearls the necklace was composed. End quote. Hindu mathematics had little direct influence upon Europe, but there is little doubt that the Arabs got their arithmetic and algebra from the representatives of Brahmin knowledge who were so liberally entertained at the courts of the enlightened caliphs of the 9th and 10th centuries. Muslim civilization of that period was the blending of 2 cultures, the Oriental and the Hellenic. The great number of Sanskrit and Greek classics of literature, science, and philosophy were translated into Arabic and avidly studied by the Arab savants. Many of these translations have been preserved and are now a fertile source of historical information. We must remember in this connection that the richest library of Hellenic antiquity, that of Alexandria, was twice pillaged or destroyed, first by Christian Vandals in the 4th century, then by Muslim fanatics in the 7th. As a result of this destruction, a great number of ancient manuscripts disappeared and would have been completely lost to posterity if it were not for their Arabic translations. It has been often said that the historic destiny of the Arabs was to act as custodians of Hellenic culture during these transition ages. This they did exceedingly well, but they also enriched the treasure by brilliant contributions of their own. I may mention among the numerous first-rate mathematicians of the period the name of one man whose fame is familiar to every cultured person, Omar Khayyam. The author of the Rubaiyat was official astronomer of the court of the caliph. Though the Rubaiyat was written in Persian, Omar wrote an Arabic algebra in which he took full advantage of his knowledge of Greek geometry and Hindu algebra to solve cubic and quartic equations. Indeed, he can be considered as the originator of graphical methods. Furthermore, there are indications that he anticipated Newton in the discovery of the binomial formulas. And yet for all this, the Arabs have not advanced one iota in symbolic notation. It is one of the strangest phenomena in the history of mathematics that the Arabs, in adopting Hindu algebra, did not retain their quaint syncopated symbolism. Quite the contrary, they dropped back to the rhetorical algebra of the Greeks, and for a time even went so far as to eliminate numeral symbols from their treatise on algebra, preferring to write numbers out in full. Was it that the Arabs pushed their claim of being the intellectual heirs of the Hellenists to the point of refusing to acknowledge the debt they owed to the Brahmins? While Muslim culture was approaching its highest point, Europe was still in deep slumber. A magnificent pen picture of these dark ages and the centuries of transition which followed is given by the great mathematician Jacobi in his address on Descartes. Quote, history knew a midnight, which we may estimate at about the year 1000 after death, when the human race had lost the arts and sciences even to the memory. The last twilight of paganism was gone, and yet the new day had not begun. Whatever was left of culture in the world was found only with the Saracens, and a pope eager to learn studied in disguise at their universities, and so became the wonder of the West. At last Christendom, tired of praying to the dead bones of the martyrs, flocked to the tomb of the Saviour himself, only to find for a second time that the grave was empty and that Christ had risen from the dead. Then mankind too rose from the dead. It returned to the activities and the business of life. There was a feverish revival in the arts and in the crafts. The cities flourished, a new citizenry was founded. Cimabue rediscovered the extinct art of painting, Dante that of poetry. Then it was, also, that great courageous spirits like Abelard and St. Thomas Aquinas dared to introduce into Catholicism the concepts of Aristotelian logic, and thus founded scholastic philosophy. But when the Church took the sciences under her wing, she demanded that the forms in which they moved be subjected to the same unconditioned faith and authority as were her own laws, and so it happened that scholasticism, far from freeing the human spirit, enchained it for many centuries to come, until the very possibility of free scientific research came to be doubted. At last, however, here too daylight broke, and mankind, reassured, determined to take advantage of its gifts and to create a knowledge of nature based on independent thought. The dawn of this day in history is known as the Renaissance, or the revival of learning." End quote. Now, the acquisition of culture was certainly not a part of the Crusaders' program, yet this is exactly what the Crusades accomplished. For 3 centuries, the Christian powers tried by sword to impose their culture upon Muslim, but the net result was that the superior culture of the Arabs slowly yet surely penetrated into Europe. The Arabs of Spain and the Arabs of the Levant were largely responsible for the revival of European learning. The revival of learning began in Italy. The first notable work in mathematics was that done by Fibonacci, a man of extraordinary ability, whose insight and foresight were far above the 13th century in which he lived. A merchant by vocation, he had traveled considerably in the Near East and had absorbed the Arabic knowledge of the period, but he was also conversant with Greek mathematical literature. His contribution to arithmetic, algebra, and geometry formed the rich source of Italian mathematics for the next 3 centuries. Of this, however, I shall speak in the next chapter. The turning point in the history of algebra was an essay written late in the 16th century by Frenchman Viète, who wrote under the Latin name Franciscus Vieta. His great achievement appears simple enough to us today. It is summed up in the following passage from this work. Quote, "In this we are aided by an artifice which permits us to distinguish given magnitudes from those which are unknown or sought, and this by means of a symbolism which is permanent in nature and clear to understand. For instance, by denoting the unknown magnitudes by A or any other vowels, while the given magnitudes are designated by B, C, G, or other consonants." End quote. This vowel-consonant notation had a short existence. Within half a century of Vieta's death appeared Descartes' geometry, in which the first letters of the alphabet were used for given quantities, the last for those unknown. The Cartesian notation not only displaced the Vietan, but has survived to this day. But while few of Vieta's proposals were carried out in letter, they certainly were adopted in spirit. The systematic use of letters for undetermined but constant magnitudes, the logistica speciosa as he called it, which has played such a dominant role in the development of mathematics, was the great achievement of Vieta. The lay mind may find it difficult to estimate the achievement of Vieta at its true value. Is not the literal notation a mere formality after all, a convenient shorthand at best? There is, no doubt, economy in writing (a plus b squared equals a squared plus 2ab plus b squared). But does it really convey more to the mind than the verbal form of the same identity? The square of the sum of 2 numbers equals the sum of the squares of the numbers, augmented by twice their product? Again, the literal notation had the fate of all very successful innovations. The universal use of these makes it difficult to conceive of a time when inferior methods were on vogue. Today, formulae in which letters represent general magnitudes are almost as familiar as common scripts, and our ability to handle symbols is regarded by many almost as a natural endowment of any intelligent man. But it is naturally only because it has become a fixed habit of our minds. In the days of Vieta, this notation constituted a radical departure from the traditions of ages. And really, how can we call natural a device which completely escaped the great Diophantus and his acute Arabian successors, while the ingenious Fibonacci was on the very brink of discovering it, but passed it up? There is a striking analogy between the history of algebra and that of arithmetic. There, we saw, humanity struggled for thousands of years with an inadequate numeration for lack of symbol for naught. Here, the absence of a general notation reduced algebra to a collection of haphazard rules for the solution of numerical equations. Just as the discovery of zero created the arithmetic of today, so did the literal notation usher in a new era in the history of algebra. Wherein lies the power of this symbolism? First of all, the letter liberated algebra from the slavery of the word. And by this I do not mean merely that without the literal notation any general statement would become a mere flow of verbiage, subject to all the ambiguities and misinterpretations of human speech. This is important enough, but what is still more important is that the letter is free from the taboos which have attached to words through centuries of use. The arithmos of Diophantus, the res of Fibonacci were preconceived notions. They meant a whole number, an integer. But the a of Vieta, or our present x, has an existence independent of the concrete object which it is assumed to represent. The symbol has a meaning which transcends the object symbolized. That is why it is not a mere formality. In the second place, the letter is susceptible of operations which enables one to transform literal expressions and thus to paraphrase any statement into a number of equivalent forms. It is this power of transformation that lifts algebra above the level of a convenient shorthand. Before the introduction of literal notation, it was possible to speak of individual expressions only. Each expression, such as 2x plus 3, 3x minus 5, x squared plus 4x plus 7, 3x squared minus 4x plus 5, had an individuality all its own and had to be handled on its own merits. The literal notation made it possible to pass from the individual to the collective, from the sum to the any and the all. The linear form ax plus b, the quadratic form ax squared plus bx plus c. Each of these forms is regarded now as a single species. It is this that made possible the general theory of functions, which is the basis of all applied mathematics. But the most important contribution of the Logistica Speciosa, and the one that concerns us most in this study, is the role it played in the formation of the generalized number concept. As long as one deals with numerical equations such as x plus 4 equals 6, 2x equals 8, x squared equals 9, x plus 6 equals 4, 2x equals 5, and x squared equals 7, one can content himself, as most medieval algebraists did, with the statement that the first group of equations is possible, while the second is impossible. But when one considers the literal equations of the same types, x plus b equals a, bx equals a, or x to the nth exponent equals a, the very indeterminateness of the data compels one to give an indicated or symbolic solution to the problem, such as x equals a minus b, x equals a divided by b, or x equals a to the nth root. In vain after this will one stipulate that the expression a minus b has a meaning only if a is greater than b, that a over b is meaningless when a is not a multiple of b, and that a to the nth root is not a number unless a is a perfect nth power. The very act of writing down the meaninglessness has given it a meaning, and it is not easy to deny the existence of something that has received a name. Moreover, with the reservation that a is more than b, that a is a multiple of b, that a is a perfect nth power, rules are devised for operating on such symbols as a minus b, a over b, or a to the nth root. But sooner or later, the very fact that there is nothing on the face of these symbols to indicate whether a legitimate or illegitimate case is before us will suggest that there is no contradiction involved in operating on these symbolic beings as if they were bona fide numbers. And from this, there is but one step to recognizing these symbolic beings as numbers in extenso. Such in its broad outlines is the story of early algebra, or rather, that phase of it which led up to the generalized number concept. We shall now have to abandon the historical route for two reasons. First of all, so rapid was the development of mathematics after the days of Vieta that the systemic exposition of it would lead us far beyond the scope of this book. Moreover, the foundation of the science of number was influenced but little by this development, as long as progress was confined to technique only. What distinguishes modern arithmetic from that of the pre-Vieta period is the changed attitude towards the impossible. Up to the 17th century, the algebraists invested this term with an absolute sense, committed to natural numbers as the exclusive field for all arithmetic operations. They regarded possibility or restricted possibility as an intrinsic property of these operations. Thus, the direct operations of arithmetic, addition, a plus b, multiplication, ab, potentiation, a to the exponent b, were omnipossible, whereas the inverse operations, subtraction, a minus b, division, a over b, extraction of roots, a to the root b, were possible only under restricted conditions. The pre-Vieta algebraists were satisfied with stating these facts, but were incapable of a closer analysis of the problem. Today we know that possibility and impossibility have each only a relative meaning, that neither is an intrinsic property of the operation but merely a restriction which human tradition has imposed on the field of the operand. Remove the barrier, extend the field, and the impossible becomes possible. The direct operations of arithmetic are omnipossible because they are but a succession of iterations, a step-by-step penetration into the sequence of natural numbers, which is assumed a priori unlimited. Drop this assumption, restrict the field of the operand to a finite collection, say to the first 1,000 numbers, and operations such as 925 plus 125 or 67 times 15 become impossible, and the corresponding expressions meaningless. Or let us assume that the field is restricted to odd numbers only. Multiplication is still omnipossible, for the product of any two odd numbers is odd. However, in such a restricted field, addition is an altogether impossible operation, because the sum of any two odd numbers is never an odd number. Yet again, if the field were restricted to prime numbers, multiplication would be impossible, for the simple reason that the product of two primes is never a prime, while addition would be possible only in such rare cases when one of the two terms is 2, the other being the smaller of a couple of twin primes, like 2 plus 11 equals 13. Other examples could be adduced, but even these few will suffice to bring out the relative nature of the words possible, impossible, and meaningless. And once this relativity is recognized, it is natural to inquire whether through a proper extension of the restricted field, the inverse operations of arithmetic may not be rendered as omnipossible as the direct are. To accomplish this with respect to subtraction, it is sufficient to adjoin to the sequence of natural numbers 0 and the negative integers. The field so created is called the general integer field. Similarly, the adjunction of positive and negative fractions to this integer field will render division omnipossible. The numbers thus created, the integers and the fractions, positive and negative, and the number 0, constitute the rational domain. It supersedes the natural domain of integer arithmetic. The four fundamental operations, which heretofore applied to integers only, are now by analogy extended to these generalized numbers. All this can be accomplished without a contradiction, and, what is more, with a single reservation which we shall take up presently: the sum, the difference, the product, and the quotient of any two rational numbers are themselves rational numbers. This very important fact is often paraphrased into the statement, "The rational domain is closed with respect to the fundamental operations of arithmetic." The single but very important reservation is that of division by 0. This is equivalent to the solution of the equation x times 0 equals a. If a is not 0, the equation is impossible, because we were compelled in defining the number 0 to admit the identity a times 0 equals 0. There exists therefore no rational number which satisfies the equation x times 0 equals a. On the contrary, the equation x times 0 equals 0 is satisfied for any rational value of x. Consequently, x is here an indeterminate quantity. Unless the problem that led to such equations provides some further information, we must regard 0 over 0 as the symbol of any rational number, and a over 0 as the symbol of no rational number. Elaborate though these considerations may seem, in symbols they reduce to the following concise statement. If a, b, and c are any rational numbers and a is not 0, then there always exists a rational number x, and only one, which will satisfy the equation ax plus b equals c. This equation is called linear, and it is the simplest type in a great variety of equations. Next to linear come quadratic, then cubic, quartic, quintic, and generally algebraic equations of any degree, the degree n, meaning the highest power of the unknown x in ax to the exponent n plus bx to the exponent n minus 1 plus cx to the exponent n minus 2, ellipses, plus px plus q equals 0. But even these do not exhaust the infinite variety of equations, exponential, trigonometric, logarithmic, circular, elliptic, etc., constitute a still vaster variety. Usually classified under the all-embracing term transcendental. Is the rational domain adequate to handle this infinite variety? We shall see in the next chapter that this is emphatically not the case. We must anticipate an extension of the number domain to greater and greater complexity. But this extension is not arbitrary. There is concealed in the very mechanism of the generalizing scheme a guiding and unifying idea. This idea is sometimes called the principle of permanence. It was first explicitly formulated by the German mathematician Hermann Hankel in 1867. But the germ of the idea was already contained in the writings of Sir William Rowan Hamilton, one of the most original and fruitful minds of the 19th century. I shall formulate this principle as a definition. A collection of symbols infinite in number shall be called a number field, and each individual element in it a number. First, if among the elements of the collection we can identify the sequence of natural numbers. Second, if we can establish criteria of rank which will permit us to tell of any two elements whether they are equal, or if not equal, which is greater, these criteria reducing to the natural criteria when the two elements are natural numbers. Third, if for any two elements of the collection we can devise a scheme of addition and multiplication which will have the commutative, associative, and distributive properties of the natural operations bearing these names, and which will reduce to these natural operations when the two elements are natural numbers. These very general considerations leave the question open as to how the principle of permanence operates in special cases. Hamilton pointed the way by a method which he called algebraic pairing. We shall illustrate this on the rational numbers. If a is a multiple of b, then the symbol of a divided by b indicates the operation of division of a by b. Thus 9 over 3 equals 3, means that the quotient of the indicated division is 3. Now, given two such indicated operations, is there a way of determining whether the results are equal, greater, or less without actually performing the operations? Yes, we have the following criteria of rank. A over b equals c over d if AD equals BC. A over b is greater than c over d if AD is greater than BC. And A over b is less than c over d if AD is less than BC. And we can go even further than that. Without performing the indicated operations, we can devise rules for manipulating on these indicated quantities. In addition, A over b plus c over d equals AD plus BC over BD. And in multiplication, A over b times c over d equals AC over BD. Now let us not stipulate any more that A be a multiple of B. Let us consider A over B as the symbol of a new field of mathematical beings. These symbolic beings depend on two integers A and B written in proper order. We shall impose on this collection of couples the criteria of rank mentioned above, i.e., we shall claim that, for instance, 20 over 15 equals 16 over 12 because 20 times 12 equals 15 times 16. 4 over 3 is greater than 5 over 4 because 4 times 4 is greater than 3 times 5. We shall define the operations on these couples in accordance with the rules which, as we have shown above, are true for the case when A is a multiple of B and C is a multiple of D, i.e. we shall say, for instance, 2 over 3 plus 4 over 5 equals bracket 2 times 5 bracket plus bracket 3 times 4 bracket over 5 times 3, which equals 22 over 15. And 2 over 3 times 4 over 5 equals 2 times 4 over 3 times 5, which equals 8 over 15. We have now satisfied all the stipulations of the principle of permanence. 1. The new field contains the natural numbers as a subfield, because we can write any natural number in the form of a couple, 1 over 1, 2 over 1, 3 over 1, 4 over 1, etc. 2. The new field possesses criteria of rank which reduce to the natural criteria when A over B and C over D are natural numbers. 3. The new field has been provided with two operations which have all the properties of addition and multiplication to which they reduce when A over B and C over D are natural numbers. And so these new beings satisfy all the stipulations of the principle. They have proved their right to be adjoined to the natural numbers, their right to be invested with the dignity of the name number. They are therewith admitted, and the field of numbers comprising both old and new is christened the rational domain of numbers. It would seem at first glance that the principle of permanence leaves such a latitude in the choice of operations as to make the general number it postulates too general to be of much practical value. However, the stipulations that the natural sequence should be a part of the field and that the fundamental operations should be commutative, associative, and distributive, as the natural operations are, impose restrictions which, as we shall see, only very special fields can meet. The position of arithmetic, as formulated in the principle of permanence, can be compared to the policy of a state bent on expansion, but desirous to perpetuate the fundamental laws on which it grew strong. These two different objectives, expansion on the one hand, preservation of uniformity on the other, will naturally influence the rules for admission of new states to the Union. Thus, the first point in the principle of permanence corresponds to the pronouncement that the nucleus state shall set the tone of the Union. Next, the original state being an oligarchy in which every citizen has a rank, it imposes this requirement on the new states. This requirement corresponds to the second point of the principle of permanence. Finally, it stipulates that the laws of commingling between the citizens of each individual state admitted to the Union shall be of a type which will permit unimpeded relations between citizens of that state and those of the nucleus state. Of course, I do not want the reader to take this analogy literally. It is suggested in the hope that it may invoke mental associations from a more familiar field, so that the principle of permanence may lose its seeming artificiality. The considerations which led up to the construction of the rational domain were the first steps in historical process called the arithmetization of mathematics. This movement, which began with Weierstrass in the 60s of the last century, had for its object the separation of purely mathematical concepts, such as number and correspondence and aggregate, from intuitional ideas, which mathematics had acquired from long association with geometry and mechanics. These latter, in the opinion of the formalists, are so firmly entrenched in mathematical thought that in spite of the most careful circumspection in the choice of words, the meaning concealed behind these words may influence our reasoning. For the trouble with human words is that they possess content, whereas the purpose of mathematics is to construct pure forms of thought. But how can we avoid the use of human language? The answer is found in the word symbol. only by using a symbolic language not yet usurped by those vague ideas of space, time, continuity, which have their origin in intuition and tend to obscure pure reason, only thus may we hope to build mathematics on the solid foundation of logic. Such is the platform of this school, a school which was founded by the Italian piano, and whose most modern representatives are Bertrand Russell and A.N. Whitehead. In the fundamental work of the latter men, the Principia Mathematica, they have endeavored to reconstruct the whole foundation of modern mathematics, starting with clear-cut fundamental assumptions and proceeding on principles of strict logic. The use of a precise symbolism should leave no room for those ambiguities which are inseparable from human language. The Principia will long remain a monument of hard labor and excellent intentions. Have its authors succeeded in erecting a structure reared on pure reason and untainted by human intuition? I am incompetent to answer this question, as I have never met a mathematician who has read all 3 of its volumes. The story current in mathematical circles is that there are but 2 people who have ever read the Principia from cover to cover. Whether the authors themselves were included in this estimate, I have not been able to ascertain. I confess that I am out of sympathy with the extreme formalism of the Piano-Russell school, that I have never acquired the taste for their methods of symbolic logic, that my repeated efforts to master their involved symbolism have invariably resulted in helpless confusion and despair. This personal ineptitude has undoubtedly colored my opinion, a powerful reason why I should not air my prejudices here. Yet I am certain that these prejudices have not caused me to underestimate the role of mathematical symbolism. To me, the tremendous importance of this symbolism lies not in these sterile attempts to banish intuition from the realm of human thought, but in its unlimited power to aid intuition in creating new forms of thought. To recognize this, it is not necessary to master the intricate technical symbolism of modern mathematics. It is sufficient to contemplate the more simple, yet much more subtle symbolism of language. For insofar as our language is capable of precise statements, it is but a system of symbols, a rhetorical algebra par excellence. Nouns and phrases are but symbols of classes of objects, verbs symbolize relations, and sentences are but propositions connecting these classes. Yet, while the word is the abstract symbol of a class, it has also the capacity to evoke an image, a concrete picture of some representative element of the class. It is in this dual function of our language that we should seek the germs of the conflict which later arises between logic and intuition. And what is true of words generally is particularly true of those words which represent natural numbers, because they have the power to evoke in our mind images of concrete collections. They appear to us so rooted in firm reality as to be endowed with an absolute nature. Yet in the sense in which they are used in arithmetic, they are but a set of abstract symbols subject to a system of operational rules. Once we recognize the symbolic nature of the natural number, it loses its absolute character. Its intrinsic kinship with the wider domain of which it is the nucleus becomes evident. At the same time, the successive extensions of the number concept become steps in an inevitable process of natural evolution, instead of the artificial and arbitrary legerdemain which they seem at first. Chapter 6. The Unutterable. Quote, God created the integers, the rest is the work of man. Leopold Kronecker. Number ruled the universe of the Pythagoreans. Not number in the modern sense of the word, it was the natural number, the integer, that reigned supreme. But neither was the universe of the Pythagoreans our universe, a universe which transcends the immediate sense perception, which manifests itself so richly, even if mysteriously, in the numerous inventions which make up the essential part of our daily life. The universe of the Greeks was limited to things more immediately accessible to the senses. In the harmonies of sound, the Pythagoreans saw a confirmation of their number philosophy. The harmony of sight and touch found supreme expression in the perfect figures of geometry. the circle and the sphere, the regular polygons and the perfect solids. Such were the elements used by the great architect in building the world. Here, too, it was confidently expected number would be found to reign supreme. Quote, "The point is unity in position," end quote, was the basis of Pythagorean geometry. Behind this flowery verbiage we detect the naive idea of the line as made up of a succession of atoms, just as a necklace is made up of beads. The atoms may be ever so small, yet being all homogeneous in substance and equal in size, they may be taken as the ultimate unit of measure. Therefore, given any two segments, the ratio of their length was merely the ratio of the numbers of atoms in each. The same, of course, was true of the sides of any triangle, particularly the right triangle. From Egypt the Pythagoreans imported the golden triangle, the sides of which were in the ratio 3:4:5. Soon other Pythagorean triangles, such as 5, 12, and 13, and 8, 15, and 17, were discovered. The conviction that all triangles were rational had evidence to feed on. That some of the triangles, most of them, in fact, did not yield such perfect ratios was not at all surprising. For after all, the ratios may run into very large numbers, and the calculating technique of the Greeks was primitive enough. So matters stood still for a while. The contemplation of such triangles led to a capital discovery, which to this day bears the name of Pythagoras, and which is one of the basic theorems of classical geometry. It reads, "In any right triangle the sum of the squares built on the legs is equal to the square built on the hypotenuse." According to legend, the theorem was discovered by Pythagoras himself, who was so overwhelmed by its elegance that he sacrificed an ox to the gods. How this legend can be reconciled with the pretty well-established fact that the Pythagoreans were strict vegetarians is left to the reader. It may be doubted that Pythagoras derived his theorem through deductive reasoning. Most likely it was an empirical product. That he possessed a rigorous proof of the proposition is just as unlikely. But there can be little doubt that he and his disciples attached the greatest importance to it, for therein they saw the inherent union between geometry and arithmetic, a new confirmation of their dictum, "Number rules the universe." But the triumph was short-lived. Indeed, one of the immediate consequences of the theorem was another discovery: the diagonal of the square is incommensurable with its side. Who it was that first established this, and how it was done, will probably remain a mystery forever. Euclid's beautiful proof, which is given below, is obviously the development of a cruder method, but whoever discovered it, there is little doubt that it caused great consternation in the ranks of the Pythagoreans. The very name given to these entities testifies to that. Allagon, the unutterable, these incommensurables were called, and the members of the order were sworn not to divulge their existence to outsiders. An unaccountable imperfection having been uncovered in the work of the architect, it must be kept in strict concealment, lest his wrath at being exposed be visited upon man. Says Proclus, quote, "It is told that those who first brought out the irrationals from concealment into the open perished in shipwreck to a man. For the unutterable and the formless must needs be concealed, and those who uncovered and touched this image of life were instantly destroyed and shall remain forever exposed to the play of the eternal waves." End quote. Less than a century passed, and the Pythagorean secret became the property of all thinking men. The unutterable had been spoken, the unthinkable clothed in words, the unrevealable presented to the eyes of the uninitiated. Man had tasted of the forbidden fruit of knowledge, and was condemned to be banished from the Pythagorean number paradise. The advent of irrationals marks the decline of Pythagoreanism as a system of natural philosophy. That perfect concordance between things arithmetic and things geometrical, which the Pythagoreans preached, turned out to be a hoax. How can number dominate the universe when it fails to account for even the most immediate aspect of the universe, geometry? So ended the first attempt to exhaust nature by number. Like most classical demonstrations, Euclid's proof of the incommensurability of the diagonal of the square with its side is of the type reductio ad absurdum. It is geometrical only in appearance, for it is based on pure consideration of the theory of numbers. In modern phraseology, each side of the square being taken as 1, and the diagonal denoted by x, Pythagoras' theorem reduces the problem to the solution of the quadratic equation x squared equals 1 squared plus 1 squared, or x squared equals 2. If it is possible to satisfy this equation by a rational number p over q, then the diagonal and the side are commensurable. Let us assume that such is the case, and that the fraction p over q is in its lowest terms. Then one of the two integers, either p or q, must be odd. I shall show that p cannot be odd. Indeed, substitute in equation p over q for x, it then becomes p squared over q squared equals 2, or p squared equals 2q squared, which shows that p squared and therefore p is even. Now since p is even, we can set p equals 2r, where r is another unknown integer. Substituting this in, we can obtain 4r squared equals 2q squared, or q squared equals 2r squared, which is of the same type as equation 2. But this means that the integer q is also even, which contradicts our assumption that p over q is in its lowest terms, which in turn shows the impossibility of satisfying the equation x squared equals 2 by a rational number. The argument is perfectly general. Slightly modified, it applies to the equation x squared equals 3, x squared equals 5, x squared equals 6, x cubed equals 2, x cubed equals 3, and x cubed equals 4. And more generally to the equation x to the n equals a, when a is not the perfect nth power of some rational number. The equation x to the power n equals a has no rational solutions. We find in the writings of the minor Greek geometers, such as Hero of Alexandria and Theon of Smyrna, approximate values for the irrational numbers root 2, root 3, root 5, etc. No mention is made as to the method by which these values were obtained, since in most of these cases the approximations were excellent. Historians of mathematics have let their imagination play freely in reconstructing the unknown methods. There are quite a number of such theories. Some credit Greek mathematicians with the knowledge of infinite series, others of continued fractions. I venture a theory of my own, which, while just as speculative, has at least the merit of not assuming that the Greeks were versed in modern methods. My theory is this. Euclid's proof of the irrationality of root 2 was, for the average Greek mathematician, too exotic to be convincing. There might have been among the Pythagorean diehards who had not given up the hope of finding a rational value for root 2, root 3, etc. The search for such rational values proceeded along most natural lines. The number 2, for instance, could be presented in an infinite number of ways as a fraction whose denominator was a perfect square. 2 over 1 equals 8 over 4 equals 18 over 9 equals 32 over 16 equals 50 over 25 equals 72 over 36 equals 128 over 64 equals 200 over 100 equals etc. If root 2 was a rational number, then by going out far enough a fraction would eventually be found whose numerator is also a perfect square. In this, of course, they failed, but as a byproduct an excellent approximation was found. Indeed, 288 over 144 equals 2, while 289 over 144 equals 17 over 12 to the power of 2. This gives for root 2 the Theon approximation 1, 5 over 12, which differs from the true value by less than 1/7 of 1%. I offer this theory for what it is worth. There is a variety of problems in geometry, some of the most simple type, which admit of no numerical solution, at least not so long as we confine ourselves to the rational domain of numbers. Take the case of a diagonal of a square of side 1 as an instance. A child who had learned the elementary constructions by ruler and compass could determine the diagonal geometrically. The same is true of other problems that lead to quadratic, cubic, or higher equations, or even transcendental equations, yet these problems escape completely the attack by rational arithmetic. On the other hand, the irrational quantities can be expressed through rational approximations to any desired degree of accuracy. The procedure we presented in the section just above is perfectly general. Procedures of a similar character are the algorithm for the extraction of a square root, which are taught in school, expansion into series, continued fractions, and numerous other devices which can be drafted into service whenever we are confronted with a problem which admits of no rational solution. Such methods enable one to trap the irrational number between two sequences of rational numbers, of which the first is consistently less than the irrational, and the second consistently greater. And what is more, the interval between these rational approximations may be rendered as small as one desires. Well, what further can be desired? The physicist, the engineer, the practical man generally are fully satisfied. What the physicist requires of his calculating methods is a degree of refinement which will permit him to take full advantage of the growing precision of his measuring devices. The fact that certain magnitudes like root 2, pi, or e are not expressible mathematically by means of rational numbers will not cause him to lose any sleep, as long as mathematics is furnishing him with rational approximations for such magnitudes to any accuracy he desires. The position of the mathematician with respect to this problem is different, and for this reason he views the rational domain of numbers as a totality, as an aggregate. He sees this aggregate extending from negative infinity through 0 into positive infinity. This aggregate is ordered. Give him any two rational numbers, and he will tell you which is the greater. Between any two rational numbers he can insert a third, and this no matter how near the two numbers may be. He expresses this in his jargon by saying that the rational domain is everywhere dense. In short, he views the aggregate of rational numbers as a compact, continuous mass, seemingly without gaps. To him, there is a striking analogy between this and the set of points on a straight line. Here too the aggregate extends indefinitely in both directions. Here too of any two elements, he can tell which is to the right. Here too he finds the property of compactness, for between any 2 points he can insert a third, and this no matter how close the points may be together. So complete does this analogy appear, that there should be a way of establishing a correspondence between the rational domain of numbers on the one hand and the points on a line on the other hand. This correspondence is the basis of analytic geometry, and even those of my readers who have never studied it have a very good idea of what it is all about from the occasional graphs they have handled. So I shall remind them only that the scheme consists in defining on an indefinite straight line a positive and a negative sense. Such a line endowed with sense is called an axis. On the axis we select 2 points, O, the origin, which represents the number 0, and U, the unit point, which represents the number 1. The positive integers we obtain by laying off to the right a succession of intervals equal to OU in length, and the negatives by proceeding similarly to the left. By dividing the unit segment into any number of aliquot parts, we are able to represent any positive or any negative fraction as well. Thus, any rational number may be represented by a point on the axis, and immediately the question arises whether the converse is also true, i.e., whether to any point on the axis will correspond to a rational number. The answer is an emphatic no, for if we construct a square of a side equal to OU and carry a segment OD equal to the diagonal of this square, to the point D will correspond no rational number. So the absence of the gaps was only a delusion. It is true that if all rational numbers were mapped on the axis, we would obtain a compact set. Yet these points would by no means fill the line. There would be left an infinite number of gaps, which would admit of no such representation. And we shall see later in what sense we may claim that the irrational gaps by far exceed the rational points. From the standpoint of the pure mathematician, the fundamental fact is this. To any rational number corresponds a point on the axis, but the correspondence is not reciprocal. There are points on the axis to which no rational number can be assigned. These points are not only infinite in number, but infinite in variety as well. Each variety, such as root a, cube root a, and n root a, etc., comprising an infinite number of irrational points. Thus, we are again confronted with the task of extending the number concept. We must push the number domain far beyond the concept of rational number. For this latter will not suffice even for the solution of the most simple quadratic equation. It is natural to invoke once more the principle of permanence which rendered such valuable service before. We create the symbol a to the nth root. This symbol represents a rational number if the equation x to the exponent n equals a has a rational solution, i.e., when a is a perfect nth power of a rational number. Using this special case as a point of departure, we establish rules for operating on these symbols. These identities are then taken as defining relations of a new number field, the field of elementary irrationals, the radicals, symbolized by a to the nth root. Thanks to the device of reduction to a common exponent, the criteria of rank are easily established. If, for instance, we wish to compare root 2 and 3 to the root 3, we write root 2 equals 8 to the root 6, 3 to the root 3 equals 9 to the root 6, 9 to the root 6 is more than 8 to the root 6. And this leads to the inequality 3 to the root 3 is greater than root 2. Multiplication and division are also easily defined by means of the same device. The product of any two surds bearing on rational numbers is itself an entity of the same type. For instance, root 2 times 3 to the root 3 equals 8 times 9 to the root 6, which equals 72 to the root 6. An insurmountable difficulty, however, is met in addition. Such an expression as root 2 plus root 3 cannot be expressed in the form a to the root n, where a is a rational number. The sum of two elementary irrationals is generally not an elementary irrational. The field of simple irrationals is closed with respect to multiplication and division, but it is wide open to addition and subtraction. To erect a consistent system, we would be compelled to extend at once our field from elementary to compound irrationals of the type a to the root n plus b to the root n. But before proceeding with such an extension, let us take a glimpse of what is ahead of us. We must not forget that we set out to solve the most general equation, ax to the power n plus bx to the power n minus 1 plus cx to the power n minus 2 plus ellipses plus px plus q equals 0, where n is any integer and the coefficients are any rational numbers. Of these very general equations, we have tackled so far the very special case of a binomial equation, ax to the power n plus b equals 0. The case n minus 1 led us to the rational domain. The general case brought in elementary irrationals. But what about the general equations? If it be reducible to the equation of the simple type x to the power n equals capital A, then its formal solution would lead to elementary irrationals. The fundamental question is this: can any algebraic equation be reduced to binomial equations? Or, in other words, can the solution of the general algebraic equation be formally expressed by means of radicals? The history of this problem provides an excellent example of the value of inductive inference. Special types of quadratic equations are found in Diophantus's Arithmetica. The theory was further developed by the Hindus, who have in connection with it established the rules for the operations on surds almost in the form in which we know them today. The task was completed by the Arabian mathematicians. The formal solution of the general quadratic equation ax squared plus bx plus c equals 0 was found to be one of the form a plus root b, i.e., it was expressible by means of rational numbers and quadratic surds. The Arabians next tackled the general cubic equation ax cubed plus bx squared plus cx plus d equals 0 with questionable success. Amr Khayyam gave an ingenious geometrical solution, but his futile efforts to obtain a formal algebraic solution led him to allege that the cubic equation cannot be solved by radicals. The problem greatly fascinated the Italian mathematicians of the Renaissance period, and it was completely solved by them in the 16th century under circumstances of which I will tell elsewhere. They found that the general solution of the cubic equation can be expressed by means of cubic and quadratic surds. Almost simultaneously, the Italian Ferrari reduced the quartic equation to the solution of auxiliary quadratics and cubics, thus proving that the equation of the fourth degree is capable of a formal solution by means of radicals, the exponent of which does not exceed 4. The natural inference was that this is generally true. The equation of degree n should, by precedent, be capable of a formal solution by means of radicals, and probably radicals of an exponent not higher than n. Such, indeed, was the general conviction of most mathematicians of the 18th century, one of the most notable expressions being Lagrange. The problem was not solved until the first part of the 19th century, as it frequently happens in mathematics. The extreme difficulty of the problem requires new methods, and the new methods turned out to be much more fruitful and far-reaching than what the problem called for. The fundamental contributions of Ruffini, Abel, and Galois not only completely solved the problem, but enriched mathematics with a new and fundamental concept, the group. It is most remarkable that two men as different in character and outlook as Abel and Galois should have become interested in the same problem and should have attacked it by similar methods. Both approached the problem of the quintic equation in the conviction that a solution by radicals was possible. Abel at 18 and Galois at 16. In fact, both thought for a while that they had discovered such a solution. Both soon realized their error and attacked the problem by new methods. In 1825, Abel proved conclusively that the general equation of the fifth degree cannot be solved by means of radicals only. He surmised that the same is true of all equations higher than the fifth. This was definitely proved by Galois. The question, what must be the special nature of an equation that it may lead to a solution by radicals, was fully answered in Galois' Testament Memoir. It is this special problem that led Galois to establish a new theory of equations, which is usually called the Galois theory of groups. This, however, is beyond our scope. To resume, then, the direct application of the principle of permanence to the problem of irrationals fails for two reasons. First, the elementary irrationals, i.e. those of the form a to the root n, do not constitute a closed field. In the second place, the compound irrational forms are inadequate for the solution of the general equation of degree higher than the fourth. To create a comprehensive theory, it is necessary to consider the entire algebraic field, a field which would contain all algebraic numbers, i.e. the solution of all possible algebraic equations. Such a field would certainly embrace the rational domain. Furthermore, it can be shown that the algebraic field is closed with respect not only to the first four fundamental operations, but also to root extraction, i.e. the sum, the difference, the product, the quotient, the powers, and the surds of any two algebraic numbers are themselves algebraic numbers. And what is more, if we consider the most general equation, ax to the exponent n plus bx to the exponent n minus 1 plus ellipses px plus q equals 0, where n is an integer but a, b, c, Ellipses, p and q are no longer restricted to being rational numbers, but can themselves be algebraic numbers of the most general type. If such an equation admits of a solution at all, the solution will be an algebraic number. Yet, comprehensive though the theory of algebraic numbers may be, it has several grave defects. In the first place, the symbolism which it requires is vague and unwieldy, for it involves all the coefficients of the equation. Furthermore, the operations of such symbols are so complicated as to make even the most simple manipulations impracticable. Finally, there is the very serious difficulty that an algebraic equation above the linear has generally more than one solution. The quadratic equation may have two. The equation of the nth degree may have as many as n distinct solutions. The ambiguity inherent in such a procedure is an insurmountable obstacle, particularly in application to problems where single-valuedness is a prime consideration. But long before the movement to generalize the number concept in this direction had gained momentum, an event occurred which eclipsed the importance even the discoveries of Abel and Galois. In 1844, the French mathematician Jacques Liouville, professor at the École Normale and founder of the important Journal des Mathématiques, read before the Paris Academy a note which was later published in his own magazine under the title "On the very extensive class of quantities which are neither algebraic nor even reducible to algebraic irrationals." In this epoch-making memoir, Liouville exhibited quantities which by their very nature cannot be the roots of any algebraic equations, and thus confirmed a suspicion which Legendre had uttered as far back as 1794. Rich though the variety of algebraic numbers may seem, they are but a province in a vaster domain, a much more extensive domain, as was shown 50 years later by Greg Cantor, who, in giving a new proof of the Liouville theorem, has put the theory of transcendentals, as these non-algebraic numbers are called, on a solid foundation. Of this, however, later. Stranger yet is the fact that these transcendentals are not just a weird product of a mathematical imagination, a dish to whet the mathematician's appetite for abstraction. The invention of the calculus brought in its wake a class of quantities which during the succeeding centuries began to play a predominant role in practically every problem of analysis, the logarithms and trigonometric ratios. Today, these quantities are in daily use in every engineering office in the world and constitute a most powerful tool of applied mathematics. In the 50 years that followed Liouville's announcement, it was definitely established that most of these quantities were transcendentals. To understand this better, let us take a glimpse at the history of the number pi. Quote, "Also he made a molten sea of 10 cubits from brim to brim, round in compass, and 5 cubits the height thereof, and a line of 30 cubits did compass it round about." End quote. Chronicles. This description of the priest's bathing pool in Solomon's temple seems to indicate that the ancient Jews held that pi, the ratio of the circumference of a circle to its diameter, equals 3. This value is 5% short of the actual. The Egyptians made a much closer estimate. We find in the papyrus Rind, 1700 BC, the value of pi as equal to 313/81, or 256/81, or 16/9 squared, which is less than 1% in excess. It is only natural that this quantity should have been the subject of speculation by the Greek mathematicians from the earliest times. But on Greek soil the problem acquired a new character. It took its place among the famous problems of antiquity, wrapped in all the legendary splendor of Greek mythology. These problems were 3 in number: the doubling of a cube, the trisection of an angle, and the squaring of a circle. The last is substantially equivalent to the determination of pi, for the area of a circle of a unit radius is equal to pi square units, and if the number pi could be expressed rationally, the whole question would be reduced to the construction of a square of a given area. In fact, if the Egyptian value were true, the area of the circle would be the same as that of a square built on 8/9 of its diameter. Around these three problems grew up most of Greek geometry. In the effort to solve them, the Greek geometers discovered the conic sections of a number of higher curves. Probably they did not suspect that a solution such as they thought did not exist. And the difficult and recalcitrant nature of the problem only spurred their efforts and drew into the arena of geometry their greatest minds, from Archimedes to Apollonius of Perga. Yet the first two problems are algebraically equivalent to the solution of the relatively simple cubic equations x cubed minus 2 equals 0 and 4x cubed minus 3x minus a equals 0, where a is a proper fraction. When we brand these problems as impossible, do we use the word impossible in the same sense as we did in arithmetic, where the impossibility was tantamount to a restriction imposed on the field? Yes, the impossibility of the classical problems was imposed by a restriction which was so old as to be considered natural, so natural indeed that it was rarely mentioned. When the Greek spoke of a geometrical construction, he meant a construction by straight edge and compass. These were the instruments of the gods. All other means were banned as unworthy of the speculation of the philosopher. For Greek philosophy, we must remember, was essentially aristocratic. The methods of the artisan, ingenious and elegant though they might appear, were regarded as vulgar and banal, and general contempt attached to all those who used their knowledge for gainful ends. There is the story of the young nobleman who enrolled in the Academy of Euclid. After a few days, he was so struck with the abstract nature of the subject that he inquired of the master of what practical use his speculations were, whereupon the master called a slave and commanded, "Give this youth a chalcus, and so he may derive gain from his knowledge." Now, those problems which are capable of a solution by straight edge only, problems which today are called linear, lead, when couched in algebraic language, to linear equations. But those which in addition require the use of the compass are algebraically equivalent to the solution of an equation of the second degree. These facts, however, were not known before the 17th century of our era. In the meantime, the two problems were repeatedly attacked by the brightest minds and by others not so bright. To this day there are professional trisectors whose greatest handicap lies in the fact that they have never learned that the problem was disposed of 300 years ago. Now, the fact that a straight-edge compass solution of a geometrical problem is either linear or quadratic does not mean that if a problem leads to a higher equation, it is incapable of such a solution. To illustrate, consider the equation x to the exponent 4 minus 3x to the exponent 2 plus 2 equals 0. The left part of it factors into bracket x squared minus 1 bracket x squared minus 2 bracket, and consequently this quartic equation really breaks up into two quadratics. Whether such a manipulation is feasible, i.e., whenever we can separate from an equation an expression of rational coefficients with a lower order, the equation is said to be reducible. The trouble with the cubic equations to which the doubling of the cube and the trisection of the general angle lead is that they are irreducible, and that this fact condemns the problems which are behind these equations as insoluble by ruler and compass. We have here another confirmation of the relative nature of the term impossible. Impossibility is nearly always the result of a restriction, usually a restriction so sanctified by tradition that it seems imposed by nature itself. Remove the restriction and the impossibility will disappear. So it is here too. It is known today that by means of special linkages, that is, instruments consisting of a series of pivoted rigid members, it is possible to solve not only these two problems, but any problem leading to an algebraic equation with rational coefficients. The problem of squaring the circle is different from the other two in that it escapes altogether algebraic formulation. Attempts to solve this problem fill the annals of mathematics since the days of Pythagoras. Archimedes was the first to recognize that the difficulty lies in the definition. When we speak of the area of a rectangle or of a triangle, we can define our terms with precision. The same is true of any polygonal figure. But what do we mean by the area enclosed within a curve? It is true that we can inscribe or circumscribe polygonal lines and speak of upper and lower bounds for such an area, but the area itself cannot be defined without bringing in infinite processes and limits. We shall see later that it was on this problem that Archimedes tested the power of the so-called method of exhaustion. Here it is enough to mention that by means of a series of polygons, some inscribed, others circumscribed, to a circle, Archimedes showed that pi was contained between 31/7 and 3/10/71. In the 1800 years which followed Archimedes, the problem made little progress. There were always, of course, plenty of circle squarers, and various alleged solutions were published, some of which were curious enough. Also, there were many approximations, among which the most interesting was root 10, probably of Hindu origin. This value, which is very close to the Egyptian, was very much in use throughout the Middle Ages. Many efforts to improve on Archimedes are also recorded. Not the least notable is that of Vieta, who used a polygon of 393,216 sides to obtain pi within 10 correct decimals. The invention of infinite processes had for result such a great refinement in calculations that Vieta's value was soon put into the shade. Today, over 700 correct decimals of the number pi are known. As to the practical value of such calculations, we leave the word to the American astronomer Simon Newcomb. Quote, 10 decimals are sufficient to give the circumference of the earth to the fraction of an inch, and 30 decimals would give the circumference of the whole visible universe to a quantity imperceptible to the most powerful microscope. From the theoretical standpoint, a possible justification may be that such laborers bespeak the refinement of modern mathematical methods. Also, there may be the forlorn hope that we may discover some sort of regularity in the succession of the decimals which would throw light on the nature of the number pi. At the end of the 18th century, the problem enters an entirely new phase. Lambert showed that pi is not a rational number, and Legendre established the fact that it cannot be the root of a quadratic equation with rational coefficients. This definitely disposed of the problem of squaring the circle, without, of course, dampening in the least the ardor of the circle squarers. For it is characteristic of these people that their ignorance equals their capacity for self-deception. There was still the possibility that pi was an algebraic number. Should such be the case, the squaring of the circle, impossible by compass and straight edge, would, formally at least, be amenable to a link-work solution. This, while of no practical value, would give a fitting climax to 2,000 years of futile effort. This possibility was considerably impaired when in 1873 the French mathematician Charles Hermite proved that the number e was a transcendental. The intimate connection between the numbers e and pi was well known, and this redoubled the efforts to prove that pi was also a transcendental number. This was indeed achieved by the German Lindemann 9 years later. This did modern analysis dispose of a problem which had taxed the ability of mathematicians since the days of Thales. So ended the second attempt to exhaust nature by number. The discovery of transcendentals, the establishment of the fact that they are far richer in extent and variety than the irrationals of algebra, that they comprise some of the most fundamental magnitudes of modern mathematics, all this showed definitely that the powerful machinery of algebra had failed just where the elementary roots of rational arithmetic had failed 2,000 years earlier. Both failures were due to the same source. Algebra, like rational arithmetic, dealt with finite processes only. Now, as then, infinity was the rock which wrecked the hope to establish number on a firmer foundation. But to legalize infinite processes, to admit these weird, irrational creatures on terms of equality with rational numbers, was just as abhorrent to the rigorists of the 19th century as it had been to those of classical Greece. Loud among those rose the voice of Leopold Kronecker, the father of modern intuitionism. he rightly traced the trouble to the introduction of irrationals and proposed that they be banished from mathematics. Proclaiming the absolute nature of the integers, he maintained that the natural domain and the rational domain immediately reducible to it were the only solid foundation on which mathematics could rest. Quote, "God made the integer, the rest is the work of man," is the famous phrase by which he will be best known to posterity. This phrase reminds me of the story of the pious old dame who was heading a committee for the erection of a new church. The architect who submitted the plans found that the old lady took the business very seriously. Most vehement was her protest against the stained glass for which his specifications called. Finally, in despair, he asked her on what ground she objected to stained glass. "I want my glass the way the Lord made it," was her emphatic reply.